Hi everybody, it's Mrs. Dinkelman, and we are in Unit 9, Differential Equations. So this first section is really just kind of a review of what we talked about in AB. And next section, we'll do a little bit more review with slope fields as well. So just some definitions here. So a differential equation is an equation that has a derivative. If we talk about the order, so like a second order means that the largest derivative would be a second derivative. And then also sometimes you'll see ours called ordinary as opposed to partial. When you get to Calc 3, you'll talk about what partial derivatives are. So first, as a reminder, just finding solutions or seeing if something is a solution just means that the original function that we have fits the description given by the differential equation. So we'll see that here in example 1. So they want us to show that that differential equation 4x squared y double prime plus 12xy prime plus 3y is 0, that this function fits in there. So what we're going to want to do is go ahead and figure out what y double prime and y prime are and just make sure that that equality, that equal sign, really is true. So let's go ahead and just do a couple of those derivatives. So think of this, I guess, to me, I want to think of this as x to the negative 3 halves as I'm taking the derivative here. So I'm just going to write those off to the side. So y prime is going to be negative 3 halves x to the subtract 1. So I'm going to subtract 2 halves. So that's going to turn that to 5 halves. And then y double prime is the next one that we'll need. So that's going to turn to positive 15 fourths x to the negative 7 halves. So let's just see if that's going to fit our description here. I know my 2 moved. All right, so I'm just going to substitute into this equation that they gave me, so this 4x squared, so it should be 4x squared, and then I'm going to insert y double prime, and we'll simplify this here in a minute just to verify that it works. Okay, so there's the second derivative plus 12x times the first derivative. And then 3 times the original function. I'm going to use the x to the negative 3 halves there. And basically the question, or what I'm verifying, is whether that truly does equal 0. So let's go ahead and simplify a little bit. So this 4 and this 4 will cancel. We'll have the 15 left over. And then remember what we do here is that we add exponents together. So this is like negative 3.5 and 2. So that would be negative 1.5. I'm going to write it like that just so I can see what's going on. Okay, in this one, let's see, the 2 and the 12 will cancel, that'll be a 6, so I'm going to have negative 18 as my coefficient, x to the, and again we're going to add exponents, so 1 and then negative 2.5, negative 1.5. So this is sort of looking promising so far that all our exponents look to be about the same. And this next one, let's just kind of convert it to the same. So negative 3 halves is also negative 1.5. And so 15 and 3 is 18 and negative 18, all like terms, they are going to be 0. And so that's true. And I just kind of like to put a little check mark at the end like, yep, I checked, and that is true. All right, the second thing we learned with differential equations is we did separable differential equations. So I use this term that I learned from a different calculus teacher. It's separate. So it's not really a word, but it's how I remember how to do these. It's really the word separate and integrate in the same word. So that's what we're going to do. We're going to separate the variables, the y's and dy's and x's and dx's, and then we're going to integrate. So for me, what I would prefer, instead of them writing y prime here on this particular example, I wish they had written dy dx right there. So now when I separate, so dy, and what I really want to do is I want to move this guy over to the other side. So I'm going to call him e to the negative y here, because what I would have to do is I'd have to divide both sides by him. I have a 2x minus 4, and if I multiply both sides by dx, that's what I'm going to get. I'm going to just simplify with one more here because really e to the negative y in the denominator means it's just e to the y. Okay, so there's my separate. And now I want to integrate. Now this is also the reason that I choose to do implicit the way I do, because you see the little dx and little dy at the end, then you know those were derivatives. and it makes sense why we'd have those at the end of our integrals. So antiderivative of e to the y is e to the y. 2x is going to become x squared minus 4x plus c. Normally what they want me to do here is they want me to solve for y and get y by itself. So to do that here, I'm going to have to natural log both sides. So let's see, we're going to have y equals natural log of x squared minus 4x plus c. Now this is what we call a general solution because of the plus c. It's not a particular, it's not the specific one they're talking about, but it's kind of a generic, our function looks like this, but we might have an extra constant there that does something with it. So same problem, example 3, what if they tell us some more information? Then we can figure out what the particular solution is going to be. So this is just f of x notation. So when y is 0, then x is 5. Okay, let's go ahead and e both sides here. I guess I'll just call that 5 plus c on the inside of that one. See if my eraser will show up. There we go. Okay, so those cancel again. So 5 plus c. So c must be -4 then. And we would just want to make sure that we rewrite that whole thing and not just say, oh, we know what c is now. We want to write what the specific or particular function or particular solution is going to be. Okay, so it's time to get to the assignment, just checking some of those differential equations, giving you some graphs to look at of differential equations, and solving some of those separate grade problems.